Number two, or using the structural hazard, using the stall for structural hazard, we resolve the issue of control hazard, branch hazard, by either stalling until the branch is known, or fetch as if nothing is wrong, and in case you fetch the wrong instruction, flush it out and fetch the right instruction. So those are the different ways we have resolved all the hazards that are in pipeline. The biggest solution for pipeline is, for every hazard, don't use pipeline. Okay? Go single cycle. Because single cycle never had these hazards before. The hazards started coming in because we started doing our instruction level parallelism. ILP. We want to execute multiple instructions at the same time. This is parallel computing, but at a single program level. One program. This is not parallel computing as if multiple programs are running. We're about to go into that parallel computing where you have multiple programs running. Our limitation right now is we have one processor. One processor, one process. That's it. You cannot run more than one. So for me to run multiple programs, I need to introduce multiple processors. That's going to be one solution. But how can I speed up even ILP a little bit faster? Instruction level parallelism, one program is allocated to the processor, and then I'm executing multiple instructions at the same time. Yes?
Can I ask a question about PS11?
PS11, sure.
So I noticed in the solution that fetch and decode did not have a problem happening at the same time, but she didn't specify that fetch and decode latches.
It's there, assuming. Did I say MIPS pipeline? It says MIPS pipeline on the top, yes? MIPS pipeline assumes you have a 5-state pipeline.
And that assumes fetch and decode latches.
Fetch decode latch is given. So if you do this, you don't have to write fetch decode latches there, unless I ask you. How are you able to do decode and fetch at the same time? If I ask you, is there a structural hazard, and how did you resolve it? Then you have to answer, otherwise you can assume it. Good. So those are the various things that we have been discussing. So let's look at one problem, which is from branching, that it is your problem set that is there. And let's see how can we solve it. So I think it's problem set 11, if I remember it. So you have a simple loop instruction in here, and just the word loop is there labeled, doesn't mean anything. We don't know whether it's going to loop or not, depends on the branch itself. So we're trying to finish off pipeline, and last topic in the branching is how can I leverage the system to correctly fetch or not fetch? Rather than stalling, rather than fetching the wrong instruction, can I set up the system so that I'm fetching the right instruction every time? Okay? So, and that's the goal for this, and this is a simple application where you have potentially, you have a branch coming in, and that will depend on what the value of R2 is. Let's initialize the value of R2 initially to 2. Now, you all should be looking at the code mentally. You know that the first time I go through the instructions, R2 will become 1. Okay? 2 minus 1, 1. And then branch on not equal, and second time it will become 0. Can everybody see that? So I'm going to go through once through the full loop, and the second time I come in, the branch will be no longer true, so I'm going to fall out, and I'm going to go to the next instruction. So there are 6 instructions. Visually you can see it in there, that R1 initialized to 2, R0 initialized to 3, R2, R2 minus 1, branch are not equal. So I have a dependency between these 2 instructions right there. So dependency there, data dependency, that means will potentially lead to data hazard. Maybe, maybe not. Okay? Maybe, maybe not. So that's one data dependency that is there. Then R7 has a dependency on, sorry, instruction 5 has a dependency on instruction 2 on R0. Instruction 6 has a dependency on that in the second instruction and the first instruction. So you can see the single pass how the dependencies are there. Now, if you look at this instruction, that currently this instruction has no dependency. Everybody sees that? R2 equals to R2 minus 1. Has no dependency. When you first time you pass by that. When I come back second time in the loop, now my second R2 is dependent on the first R2. Okay? My second R2 is dependent on my first R2. So first time I have no dependency, but second time I have dependency in the loop. So second time of the instruction execution, R2 has a dependency on R2 from the previous loop. So that's a reverse dependency in the instruction that can happen only if you have branches. So just be mindful of that. That you can have dependency straightforward and the reverse dependency. So in here, I'm going to do a fetch decode exec. No op, right back. Fetch decode exec, no op, right back. And then I'm going to do fetch decode exec. While I'm doing fetch decode exec, for the third instruction, and then no op, right back, I'll have the value of R2. I'm going to fetch decode. And at this point, because I have a data hazard, I need to worry about I have a data dependency, I need to worry about the data hazard in the system. So I know that once I decoded it, I need the R2 from the previous instruction that is not yet complete, but its instructions result set is available to me after the end of the exec cycle. In that case, I'm going to use the data forwarding to use the value of R2, exec it, and no op, and we'll see what happens to the branch. While the branch is executing, I'm going to fetch the next two instructions because that's what the system says. Because at the end of this exec, I will know whether I have the right instructions in the system. I don't have the right instruction in the system. So this is the branch that we've been looking at up to now. So 1, 2, 3, 4, 5, 6, and by looking at that instruction, you know that 5 and 6 are wrong instructions, currently fetched. I will need to flush it as soon as I'm done with the exec. That's the solution we've been looking at up to now. So we are going to change the system to tell the pipelining that whenever you see a branch, you should do this, always. You know what the value of the branch will be, every time. Now there are two options when you hit a branch. Only conditional branches, jump doesn't have two options. When you hit a conditional branch, either you're going to take the branch, or you're not going to take the branch. Those are the only two options. So if I can tell the system that whatever happens in reality, every time you decode an instruction that is a branch, you're going to do this every time. What is this? You're going to take the branch every time. Okay, that's a default. That don't worry about what happens in reality. Your default behavior, whenever you see branches, you're going to take the branch. So I am going to set the value of branch to be taken. Yes?
This is because, like, while, this is for while loops and for loops, so it's usually.
For anything, for any branch.
No, but like the logic behind it being default, is it because?
Let's get there.
Okay.
1 second. So this is a simple one loop, doesn't help. But if you have multiple loops, then definitely. So I'm going to set the flag in the system called branch flag, which says whenever you see a conditional branch, your job is to take the branch. What will happen eventually is you may not take it, but the default behavior for you should be you are always taking the branch. So by setting the value to be taken, what am I telling the system? You encountered a branch. Okay? Branch are not equal, R2 0. If R2 is not equal to 0, go to loop. That will be the evaluated value. But because the value is set to taken, that means you see a branch, you're going to go to the branch automatically. So this is saying that, oh, yes, it is a branch. Where should it go? It should go here. Okay, it should go here, so I'm going to go to that particular PC and get the next two instructions, which are 1 and 2 this time. Okay, 1 and 2 this time, not 5 and 6. Because previously we didn't have such concept called default behavior. Okay, that every time a branch is shown, you are going to take the branch. Any questions on that up to now? That's just very high level. Default behavior, you see a branch, you take it. What if you don't take the branch? Then you made a mistake. Okay? Then we're going to learn how to fix that problem, but because I know that the first time I'm correct, but the second time I will not be correct. How do I fix that? Yes and then yes.
So we do that directly under the decode?
Right after the decode, yes.
Okay.
So that's when I know that's the branch.
That was my question. So does the value in the decode get forwarded to the PC of the next instruction?
Remember, this is a label. The label has a value.
Yeah, that's what I meant.
Yeah.
So it gets, in the decode stage, it gets forwarded.
Right away, you'll take the loop and you will
Okay,
update
so it
it.
doesn't even get to the.
Doesn't even get it, correct. Good? So now, first round. Default behavior is taken. First round that I go through the instructions, I do 1, 2, 3. I come to 4. Value is 1, R2 compared to 0, branch are not equal. I'm going to go to loop. That means these are the instructions. Perfect. I will continue executing that. That's good. Then I'll go to 3, 4 again. Second time. So 1, 2, 3, 4. Second loop, I'm going to do exactly the same thing that I did. Fetch, decode, exec, because it's an instruction. I don't know that's a branch until I decode it. So second time I'm there, I decode it, it says, oh, it's a branch. What do I do whenever there's a branch? I take the branch. Okay? I take the branch every time. That's the behavior that has been set up. So I'm going to fetch 1 and 2 again. During the second loop. Now at the end of exec, I'll find out what I just did is not correct. Okay? The default behavior of taking the branch is not the correct behavior. So if this results in not taking the branch, that means the reality of execution does not match the default behavior of the branch, and they're in conflict. That means you have wrong things in the pipeline. You must flush it. And fetch the right instruction. Fetch the right instruction, because if you recall, without that branch, what was I doing? First time I did 5, 6. That was wrong. But even without the branch prediction, second time 5 and 6 are correct. Everybody sees that? So even without that default behavior, first time the loop is wrong. Second time, the loop is correct. Now this is one loop. Think of this, as somebody was mentioning earlier, what if it's a for loop? What if it's a while loop of 600, 800, 1000? So if there are 1,000 times I'm going to do the branch, over and over again, and if I have the right value for that default behavior, I will not fetch wrong instructions except for one time. Okay, only the last time I'm going to fetch the wrong one. This concept of fixing the branching, so fixing the control hazard, is called branch prediction. I'm predicting the branch before the branch happens. In that case, I'm one of those new predictors. Very optimistic. Every time I see a branch, yeah, you're gonna take it. Even if you made an error, yeah, you're gonna take it. So you don't change your predictor. You don't change your prediction. So really bad gambler, think of it as, is betting on the same thing over and over again. saying, are you gonna take the branch? Yes, you will. But you didn't take it last time. I don't care, because I only have one value for prediction. Predictor is easy to implement, and it's called a static predictor. It doesn't change. Okay, it doesn't change based on the actuality or the reality. What do I mean by reality? Reality is known once the branch is executed. Remember, I found out that I didn't take the branch? That's reality. In this case, I did take the branch. That means my prediction and reality matched. So as long as my prediction and reality matches, I'm doing good prediction. If they don't match, I'm doing bad prediction. Doesn't mean anything for this kind of predictor because it's a static predictor. It doesn't change based on the reality. Yes?
So the branch prediction, is that decided by the operating system?
It's a hardware. I'm dedicating a piece of bit per processor per execution, per process for the execution. During that execution, I'm going to set the value of that bit to be either taken or not taken. And it doesn't change. Okay? Static doesn't change whether you make a mistake or you don't make a mistake.
So that will always be it, set?
That's it.
Once the computer's created, like,
Once the program starts, once the computer starts, it's a piece of hardware. Literally, I'm dedicating a register. Extra value needed, but if I do right predictions, I can save a lot of cycles. Because as you saw, if it's a for loop, I'm not going to fetch wrong instruction X amount of time. Only one time I'm going to fetch the wrong instruction. So think about, I think this was a problem set 1 had it, that loop, when we calculated the CPI. So it was 602, I think the instructions, or 802, whatever the number was depending on you. All those instructions are looping. They are branch. And if I had a right predictor in a pipeline, they will always execute correctly except for one last time. Okay? One last time. Good or bad news about static predictors? Static predictors are easy to implement. Okay, you set the value, it doesn't have to change. You make a mistake, you flush. That's okay. Which is like having no predictor at all. But if you make the right prediction, you are saving 2 fetches, incorrect fetches, potentially. Okay? For that correct prediction, you're getting the right instruction over. So that means to be mindful that why do I need predictors? Because if the predictor is correct, I will save time. Fetching 2 instructions is not that much trouble. You know, this is the last week of the classes, then what's the impact on execution is, fetching the instruction. Because I have to go to main memory. So that's 60 nanoseconds that I'm spending going to main memory. What if I don't have to go? For every loop, you're reducing that. That's a lot of time saved for instruction execution. So, solutions to control hazard. Third solution, branch prediction. Okay? Static is good, doesn't change, easy to implement, but doesn't change. Even if I make mistake 20 times, it doesn't change. Okay, what if I keep predicting wrong? Here, I have one branch. What if I have branches all over? Okay, so one branch was correct, the next one is incorrect, the next one is incorrect, but I keep predicting the same thing over and over again. So we need to change our nature of branch to a little bit dynamic. Learn from the execution. Learn means somebody has to update it. The processor needs to update that bit every time the prediction is incorrect. Okay, prediction is correct or incorrect. So dynamic, simple, 1-bit predictor. It's 1 bit, that means it can take 2 states. Okay, it can take 2 states, either taken or not taken. Most of the time, predictors are initialized to be the optimistic value. If you're going to see the branch, what will happen? You will take it most likely. Here, even though there are 2 states, this is never used. This is for benchmarking only. Because it doesn't change, why would I even want to use it? I'm not learning from my mistakes. So this is used for benchmarking purposes, but in reality, dynamic is the only thing that is used in the system, and they are initialized always to be taken initially. Doesn't have to be. It's just a bit. I can make it 0, I can make it 1. But if it initialized to taken, and the reality is that I did not take the branch. Initial value of the predictor was taken, but when I executed the exec for the branch, I found out I didn't take the branch. My next prediction will be changed to not taken. That's how I change the state from taken to not taken. If it initialized to not taken, but the reality is taken, I flip the next prediction. Okay, I flip the next prediction, but if I keep predicting correctly, I don't change the prediction. If this was taken, keep on taking over and over again. Similarly, not taken, you do not change the state. Okay? This should look familiar to a lot of you. If you're taking Kent, Barclay, nightmares coming in? Okay? Finite, state, automata. 2 states, depending on the input, you're changing the state. Where's that coming from? From computer architecture. Same concept that you're learning in that finite state machines, you're using it here. And we are going to change that also from 1 bit to 2 bits to 4 bits to 8 bits. And the number of states keeps changing. Yes?
You said it's that dynamic is initially set to taken. That's not the same case for static, right?
There has to be some value set. So either you can be completely negative in your approach or completely positive in your approach. You have to have one.
Yeah.
Most of the time, it's set to taken because why am I using branch predictions? Because I'm anticipating branches. If I'm anticipating branches, that means I should predict it to take it. And if I don't take it, I flip it.
Gotcha.
Okay? Yeah.
Kind of just a little backtrack a little bit. So when you were looking at the code here and you said with the loop, we can have a data dependency R2 on itself in the previous iteration. Let's say if that iterated like that, did the loop for 100 times, would that say if there was a question, how many data dependencies?
If data dependency is between instructions, not how many times it is.
Okay.
Okay? Because every one of those iterations will cause a hazard for you. So if you're going through 500 loops, every time you have a hazard, your data dependency is only once.
Okay.
Okay? So that's your branch predictor, static, taken, not taken. So let me give you an example. I think this is from your last year's exam. So you have, let me explain what you're reading. What this is saying is that you have executed some program, and that is the behavior that you have noticed for the reality of the branches. Every time you executed the branch, that's what happened. Okay? Taken, not taken, 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 not taken, not taken, taken, not taken, taken, taken. Okay? So that was the reality. When did the reality happen? After the exec. Branch prediction happens in the beginning. In the beginning, so if I have static branch prediction, and I initialize that to taken, for each of those executions, those are the realities. This is what happened when I executed the code. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 predictions. Static. It never changes. Every time I'm predicting, taken. Okay? So, these are the predictions. For every time I hit the branch. Are my predictions good or are they bad? You know, what is the accuracy of my prediction? So first time that I predicted, it matched. The actuality matched the prediction. Second time, didn't match, matched, didn't match, matched, 1, 2, 3, 4, 5, 6. This is my prediction accuracy. 6 out of 10. 60% of the time, my predictor is correct. Previously, it was 50-50 when we didn't have predictor. Either I'm going to get it right or not get it right. At least now I have some benchmark. Okay? And static predictors are really good for things like for loops. When you know it's a finite times you're going to run it. So everything will be same, true, 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 and only one time will be wrong. It's not good when you have if A less than B, do this, else do this, and when you have all those varying branches, conditional branches, too many, then static is not good. So let's look at dynamic and initialize that to take it also. Dynamic senses, remember what we said about dynamic? If you make a mistake, you switch the state. On wrong input, the branch prediction changes. If you have correct input, stay in the same state. So you predicted, taken. Prediction is always first, because you don't know the reality until you execute the code. So the reality is you predicted, taken, reality is taken, your next prediction is still taken. So when the execution matches the prediction, you keep the same state. My prediction is taken, but the reality is not taken, I made a mistake, I'm going to flip my prediction. Okay? I predicted taken, I didn't take the branch. Because in reality, it was not taken. So you flip the state. You predicted not taken, reality is taken, you made a mistake again. Prediction is taken, reality matches, correct prediction, stay in the same state. Okay? Stay in the same state, and then wrong, correct, 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 correct. Did I do one extra? Take it. Point is, as you're executing it, you are flipping it every time you get it wrong. So wrong prediction results in, I have to check the bottom 3, just to make sure that I got it right. Whenever you are executing it, you predict first. You predicted taken. Reality was taken. It matched. You stayed in the same state. Okay, you didn't change it. Next was, first instruction done. You predicted again taken, reality was not taken. It did not match. So wrong, you flip the prediction next time. Next time is not taken, reality is taken. Reality doesn't match the prediction. You got it wrong, you flip it to taken. That prediction, fourth one, matches the reality. You stay in that state. You predict it to be taken, reality is not taken, does not match. You made an error, you flip to not taken. Then, predicted not taken, reality is taken, matches, right prediction, you stay in that state. Prediction is not taken, the reality is taken, doesn't match, you made an error, you flip. Do I have it correct?
No,
What is that?
it was not taken.
1, 2, 3, 4. Not taken, not taken, taken. And then does not match. Okay. So, not taken next, does not match the taken. Flip it, next is taken, does not match, flip it, taken matches. You stay in the same state one more time. Keep in mind, dynamic has one extra state. Potentially a change state or an extra state. Okay, yes?
I'm confused on the bottom one, where they weren't equal, you put a check mark and then we flipped.
Check mark from last time. It's learning from its mistakes. But it's learning too quickly. Okay? It's learning from its mistake, but it's learning too quickly. It changes its mind as soon as it makes one mistake. Okay? Not a good predictor that you predicted taken, and then, oops, made a mistake, oh, let's change my mind. Let's change my mind again. You can see it can be flipping between taken and not taken so often. Because every time it gets it wrong, it will change the prediction. It will change the prediction too fast. Okay, so it's a good start for prediction, but not really good predictor. Because I want a predictor to make few mistakes before it changes its next prediction value. So 1 bit predictor is not enough. Because how much can I save? How much can I store in a 1-bit predictor? Only one last value. Okay? Because either I made a mistake or I didn't make the mistake. If I didn't make the mistake in my prediction, what will I do? I'll keep the same prediction. If I made a mistake, I'll flip the prediction. So 1 bit can only have 2 states. I need to make mistake many times before I change my mind. So we are going to add 1 more bit. Okay, 1 more bit to our predictor so that we don't change our mind so quickly. We take our time a little bit in changing our mind. For each of the state in the question.
Yeah, for the static one, it's just set that way that it doesn't take space.
What does static mean?
It cannot change.
It cannot be changed, but it does take a bit.
Okay.
It's still 1 bit. It just stays whatever the value initialized to.
And the other one just getting.
This one, it flips based on the previous execution. Dynamic, 2-bit. Okay? 2-bit is also dynamic, but I'm going to learn my lesson not so fast. Don't change the your prediction value so quickly. Make mistake at least twice before you flip the predictor. Okay, so you are going to have taken and not taken, but now you're going to have 2 states for each of them. You're going to have strongly taken, weakly taken, weakly not taken, and strongly not taken. 4 states. First 2 states tells you the strength of the predictor. Is it a strong predictor or is it a weak predictor? Doesn't mean anything from the prediction perspective. Whether it's this or this, they're both taken values. Okay, they're both taken values. Same thing with not taken. Weakly not taken or strongly not taken, they still have the state of not taken. So if I have a prediction value of strongly not taken, so this is, you can think of as 0, 0, 0, 1, 1, 0, 1, 1. That's how you're going to implement it in the system wise, from the bit wise. Here, you have 0, 1, that's it. 1, 0, you keep flipping it. So how do you implement a 2-bit predictor on the architecture? You use 2 bits and keep flipping the bits. So when do you change the state? You change the state when you make an error. When do you make an error? When you predicted wrong. So from strongly taken, if the reality is not taken, I'm going to flip my predictor to be less strong, weakly taken. From the weakly taken, if I predict 1 more time, twice I made an error, now my predictor is weakly not taken. It's not so strong. Yes?
What is WT? Stands
Weakly taken. Strongly taken, weakly taken.
for weak.
Yeah. So not taken twice mistake, then you change it to not taken. If you predict or reality is not taken, that's not wrong now. Completely not taken, if I did not taken, twice predicted right now. Because that's a right prediction in right order. Okay, unlike here, I was keep flipping it, completely not taken on an input off, not taken, the predictor is strong now. So how do I go backwards? Same thing. From strongly not taken, if you made a mistake once, twice, not a mistake, but good prediction. From weakly taken to again taken. But if you are aim strongly taken and you keep taking the branch, you stay in the strongly taken. Yes,
So say we're on strongly taken and we have like a couple of takens,
let's look at it.
but then we get one non-taken and we immediately go to weakly taken?
No, if you're in the strongly taken,
Uh-huh.
what's the input?
We would have to loop back to.
No, what's the input you gave me? So the prediction was strongly taken,
And it was taken.
and reality was
Taken.
not taken. I'm not flipping it to not taken right away. Our predictor is no longer so strong, it's on the weakly taken.
Yeah, that's what I meant. So if we're on strongly taken and our input's taken, so let's say we loop a couple of times, and then once we hit one non-taken, then we
It's
immediately
still
go to weakly
taken.
So it doesn't matter if we had a bunch of takens first.
It doesn't matter. Correct. I don't have the previous states.
Yeah,
Because
okay.
even though 2 bits are there, I'm still doing one, over and over
I
again.
thought we had to like go.
You wait till you go back, correct? Okay? So let's see how this one performs, or how does it work for that actuality that we have it there. So that's the reality that will happen once we start to execute. But let's grab our predictor, initialize the predictor to be strongly taken. Same thing as if I had initialized it to be taken, because if I had 1 bit, now I have 2 bits, so I'm initializing that to be strongly taken. So I'm going to predict that I am going to take the branch. That's my prediction. That's my reality. I predicted strongly taken, and I did take the branch. I correctly predicted, so I stay in the same state. Okay, I stay in the same state, according to my state diagram, that on an input of same prediction, you stay in the state. Next is predicted strongly taken, but in reality you didn't take the branch, so you made an error. Okay, you made an error. In a static one, you would have flipped right away. Here, you're going to say, it's still taken, but I'm not so sure. Okay, my next prediction is still taken. It's a weak prediction. When I do that, that's the prediction, that's the reality. Correct? So, my prediction is back to strong. Okay, that I made correct prediction. Prediction is strongly taken, reality is taken, I stay in that state. Okay, I stay in that state. I predicted strongly taken, reality was that you didn't take the branch. Next one is weakly taken. You predicted weakly taken, but you didn't take the branch. You made an error. Next is weakly not taken. You made an error twice on prediction, so now you are on the not taken side. Prediction is weakly not taken, reality is taken, you made an error. So next one is weakly taken. Prediction is weakly taken, reality is not taken, made an error, weakly not taken. Prediction is weakly not taken, Reality is taken, next one is weekly taken. Prediction is weekly taken. Reality is taken, correctly predicted. Next prediction is strongly taken. I'm done, so I'm not gonna use it, but there is an extra predictor value.
So strongly taken.
Let's go through that one by one. Initial value, now that you've copied it, understand it. Initial value was strongly taken. That was the prediction. My predictor was set to strongly taken, and I started executing the code. When I started executing the code, and I hit the first branch, I took the branch. My prediction was, you are going to take the branch. Reality, prediction matched. I stayed in the same state for the next prediction. Any questions on that? Everybody's good with that? Second line. Second predictor said, you're going to strongly take the branch. When I hit the second branch, reality was that I didn't take the branch. My predictor and my reality didn't match. I made an error, okay? But I'm not changing my predictor so quickly. So I'm going to say the next prediction is still taken, but I'm no longer a strong predictor. It's a weakly taken predictor. Thus, the next predictor is weakly taken. When you make an error in the prediction, then you change the state. Predictor is weakly taken, but it's still taken. Keep in mind. Okay, even though it's not strong, but the state is still weakly taken. So then, reality hit, you took the branch, now your predictor from weakly taken became strongly taken. Because you made right prediction. You moved towards the right direction that way. Then you have, the predictor is strongly taken, reality is taken, your next predictor is stay in the same state, because you're making the right predictions. When you get to the strongly taken, next prediction, when you execute the branch, you made an error. When you made an error, the next predictor is no longer so strong. It's a weak predictor, but it's still a taken predictor. And the reality happens, you made an error again, twice taken predictor were wrong, so now you flip the state to not taken, but it's a weak predictor. It's not a strong predictor. Predictor, weakly not taken, reality taken, you made an error, you flip it to weakly taken next. Weakly taken is the predictor, reality is not taken, you flip it back to weakly not taken. Weakly not taken is the predictor, the reality is taken, you flip it to weakly taken, reality is taken, you go to the end to be strongly taken. Question?
So that's we have the one extra.
We have one extra, because the predictor will have a value at the end, always. Any other question on this? Yes?
So, when you say the prediction accuracy, what would it be?
Every time I got it right.
Huh?
Every time I got it right.
No.
Every time I got this right. Accuracy did, the formula for accuracy didn't change. How did I calculate 6 over 10 before?
So you got 6, right?
So how many I got it right now?
You asking me to calculate?
After you tell me how many I got it correct.
You got 4.
4 out of 10. That's an accuracy.
No, I was asking this, the extra ST, I don't know if that includes
ST, states have, predictor state have nothing to do with accuracy.
it. Okay.
Accuracy is the prediction accuracy. Did I predict it correctly or not? And you're looking at one set of code to compare 4 of them. If you looked at this, which one has a better accuracy?
6.
Yes, 1 bit. But that's for one execution. Overall, when you keep executing it, dynamic 2-bit does perform better than 1 bit. Yes?
So the accuracy kind of like depends on what the initial prediction is, if it's strong.
Initial and execution.
Right, so,
So if I run 1 million branches, various branches, same instruction for different predictors, and I'll figure out which one is good.
and is there like a certain prediction that's usually best for most programs, or just?
Dynamic,
depend on the program?
2-bit. Initialize, 2, take it.
Strongly taken or weakly?
Strongly taken.
Gotcha.
Because you're gonna set the value to be 0, 0 or 1, 1. How do you set the value in the middle of the execution to 1, 0 or 0, 1? Based on what? Because this is your those are your state you're changing as you're going through it. So you can't say, I'm setting it 0, 1 based on what? You have no history. So you set it to be strongly or weakly, I have no history. Let me give the benefit of doubt. That either you're not going to take any of the branches or you're going to take the branches. Always. Yes?
For this extra bit, it's just like, I'm curious to know, is there only one place that this state is stored in? Like, if there's another for loop happening, will it start at strongly?
It's per process. Per process.
Yeah.
So whatever this is, what do you think these are?
Also, it goes out of scope. If it-
No, what do you think these are?
These are actually what happened, like
What do you mean by that?
lines of code,
Lines of code. What kind of code are they?
branch instruction.
They're branches. Can they be for loop, while loop, do while, if? I don't know what they are.
Yeah.
It could be any of them. So they stay there for that program. For next program that when it's loaded, the value is reset. Because this program prediction has nothing to do with the next program prediction. Because it's only my code that is going to result in the coding.
And this is always declared at start.
It's at the hardware level.
Say it again.
It's at the hardware level. Either you have a predictor or you don't have a predictor.
Okay.
So if you have a predictor, which most modern architecture have it, it's going to be initialized to 1, 1, 0, 0, and then you use it throughout your code.
Okay.
So now that you know how predictor works, look at the problem set that is asking for prediction accuracy, so you know it makes sense to you. Okay, this was like about what, 20% for the last year's final. But if you get this wrong, I don't know what to say. But this is like the easiest question to not get it wrong. Okay, like, can you handle the accuracy of the predictor compared to the reality and make sure you can figure that out? And I think only way you're gonna get it right is practice, practice, practice. Yes?
I don't understand the last extra bit. Why is it set to strongly taken?
What do you mean?
What is the end? What is that? At the end.
She's talking about the last strongly
You
taken.
circled it.
Trust me, I can hear her. Why are you changing it? You were okay with this changing throughout, but you're not okay with that. Why not?
Because we already not assigned, we like checked every.
How do I know the program is ended? This is just a branch, correct? Those are just branches. Can I have more code?
Yeah.
I don't know what that code is. It's not branch, I know. I don't know what the code is. The program hasn't ended yet. So every time you get it right or wrong, you update the predictor, regardless of.
To whatever it was in the beginning.
No.
What?
How did you get strongly taken from here? I just went through it. You had a weakly taken predictor.
Next.
No, last one. The reality was taken, I predicted it correctly. Weakly taken, predicted correctly, that's how I became strongly taken.
The next.
Yes. Not matching. If I had it wrong, what will happen? It'll go to the weakly not taken.
That was my question.
Yes.
Understood.
So there will be always an extra value. I don't know if I'm going to use it or not. That extra value is not part of the prediction accuracy. Keep that in mind. Okay, because when I'm calculating accuracy, I'm calculating accuracy for these branches, not for the predictor. There's one extra prediction, it will be there because it's dynamic. Static do not have extra prediction because static never changes. So static, 1 bit. Dynamic, 1 bit. Dynamic, 2 bit. Those are the predictors used. And they will be the predictor that will be used in the code that we are going to execute for the purposes of pipeline. So if a pipeline code has predictor value set, make sure you know how to use it. Going back to the code that we were looking at earlier. Remember, we had a 1-bit predictor, taken. What if it was a strongly taken predictor? What if it was set to weakly not taken predictor? What will be the behavior? Okay? And those are the how the predictors are used. So branch prediction is used to speed up pipeline, but my predictor can still be wrong. And nothing wrong with that because the goal is less than single cycle execution. And if I fetch the right instruction, wrong instruction, I'll just flush it out. Instruction level parallelism. Okay? ILP is great because I am executing multiple instructions at the same time. The concept of execution of an instruction changes from single cycle to pipeline slightly. In single cycle, every instruction is always executed. If you fetched it, it will execute. Okay? You remember that? Single cycle, I never fetch a wrong instruction. Because by the time I hit the branch, I know what the next instruction will be. So I always fetch the right instruction, so if the instruction has been fetched, it will be executed. In pipeline, we have a concept of fully executed instruction. It's different from instruction execution. And the reason for that differentiation is because I can fetch wrong instructions sometimes because of the branch. So when we talk about pipeline, for pipeline performance, we're only looking at fully executed instruction. Those instructions that complete. If you just fetched it and decoded and you flushed it, those are not fully executed instructions. So keep that in mind when you read it in the notes or when you see it, fully executed versus executed. What does that mean? Executed means I was just fetched it. I didn't complete it. The instructions that are not fully executed do not impact the pipeline total pipeline time because they are overlapping with other instructions, so I'll be okay in overall. But ILP is still one program, multiple instructions. Up to now, from lecture 2, we've been looking at the same processor, the basic processor that we have. Nothing has changed about that processor. The processor we have modified it to add fetch decode latch at maximum. Okay? We added cache to it, using secondary memory as a virtual memory for it. But the processor design hasn't changed. And we have modified that processor to not only do single cycle, but also do pipeline. The processor that we've been looking at up to now, it's called a scalar processor. Scalar processor, C-A-L-A-R, scalar. One instruction is fetched at one time. That's it. Okay, one fetch, decode, exec, mem, write back. I'm not going to fetch 2 instructions at the same time. I don't have the capacity to do that. Okay? I don't have the piece of hardware to do that. To be able to fetch 2 instructions at the same time. Ability of a processor to fetch 2 instructions at the same time requires major modification to the system. Okay, it's not straightforward because as we have learned up to now, we have one IR, we have a fetching unit, we have one program counter. And so how do I do that? How do I figure out fetching multiple instructions? Number 1. Number 2, fetching multiple instructions is still ILP, instruction level parallelism. One program will be executed fast. Okay, one program will be executed fast. So how does that work? You all have heard something called multi-core. Anybody hasn't heard multi-core? Anybody has heard it? What's a multi-core? Anybody knows? Yes?
I thought it was an embedded hardware.
It better be. This is 3 days before the class ends. So,
But I don't know exactly what it is.
so multi-core, what does that mean?
Isn't it a processor?
What do you mean?
Multi-core processor can handle multiple stuff at one time.
How many processors? Is it a processor or multiple processor? So multiple processor. And what does a core means? Multiple processor?
Core is where
What's a core? Anybody else?
Base.
Nothing to do with English. If you try to translate that from English to hardware, that will not work. Yes?
I'm assuming, I think the core would be all the parts necessary to execute an instruction. So ALU,
But when I say multi-core, what does that mean to you?
Multiple, like, so multiple ALUs, multiple, I'm assuming like.
How many processors?
Sorry?
How many
One
processors?
processor?
One processor. One processor, that's it. If you have one processor, how many processes can you execute? One, that's it. So you can have a multi-core system with 8-core Intel i9 1115. Who gives a shit? That's just marketing. Okay? If your program is not able to utilize all those cores, when that program is running, that one program, it's only using one core. Rest of the 7 cores or 15 cores are just sitting there. So what is multi-core? From day one till now, you've been looking at a system, one processor with one core. That's the system that we've been looking at up to now. We are going to change this to a multi-core system. Okay, where we have 4 cores in a single processor. Important thing is, it's a one processor. What does that mean? The processor is connected to outside using the bus. Inside the bus, I have multiple cores. And we'll define what that core means, truly. It's a really a good marketing term that Intel, AMD, and not uses it. But this connection that we have to main memory is still processor to main memory. That doesn't change. Okay? So within that one single processor, you have multiple entities competing to do things for one program via the bus. Okay, via the single bus. Before I had one instruction at a time for one program. Now I can have potentially instruction 1, instruction 2, instruction 3, instruction 4. 4 instructions being fetched at the same time. Okay? Potentially. So for a few seconds, just understand the hardware. So we are going to change it completely in a second. For me to fetch 4 instructions, okay, you can figure that out that I need 4 IRs at minimum. But I need to bring them back. Okay, I need to bring them back. The problem is what's connected to the main memory, the bus. How do I get on the bus? Using the same entities, MDR and MAR. MDR, MAR, and control are still one. Okay, it's still one. The reason it's one is because there's only one way to go to main memory and one way to come back from main memory. If I have multiple MDRs, I don't know who is going in what way. There is no flow. The good news about MDR, MAR, and control is what? Once I'm on the bus, it's sequential. The way the request went in, that's the way it will come back. So going to main memory is not the problem. What I need to control is, before I jump on the bus, that the MDR and MAR, they're not getting overwritten. Okay, they're not getting overwritten as I'm pushing things during the fetch stage. Only thing I'm doing is fetching right now. Okay, so I can have 4 IRs on the processor, but as the instruction, understand first. Stop copying for a second, please. Telling you, if you understand it, you will have no questions in a second. As I am coming back from main memory, I'm going to bring the first instruction in MDR. I'm going to push it to 1 IR, second IR, third IR, and fourth IR. That's great. I have 4 instructions in the 4 IRs. You know how fetch works, all of you. Fetch works, you fetch the first instruction, you increment the PC. You fetch the next instruction, you increment the PC. This is the same program. Okay, this is the same program that I'm executing. I fetched 4 instructions, so somehow I need to account for PC incrementation differently for that program. Because I'm going to fetch 4 instructions, I only have 1 program counter. Okay, I only have 1 program counter in this multi-core system, so I need to figure out how do I change the value of PC so that I am fetching 4 instructions almost at the same time. You all remember how much time it takes to increment the PC? 1 nanoseconds. Okay? Compared to overall fetch, which is what, 33? How much did we say, 33 nanosecond? So I can balance that. I can say, put the value of PC in MAR, go start fetching. And I'm going to increment the PC right away before I do the next fetch. So my fetch, instead of at the end, will need to move first. Because otherwise, I cannot do this. This is what I'm trying to do here right now. Fetch 4 instructions in one cycle. Okay? Every instruction fetch must be from a program counter. So you fetch the first instruction, then increment the program counter, increment the program counter, increment the program counter, so on and so forth. But there's a limitation, there's a problem, because I'm trying to do 4 instructions at the same time. There is slight delay in these fetches. Slightly offset by 1 nanosecond to increment the program counter for every other fetch. Okay? So there will be a delay, slight delay before I fetch the next instruction. Even though I have 4 cores, and in those cores I have IR. That's the only thing I have introduced. Instruction register. Yes?
What if, like, you see how we're fetching 4 instructions at the same time? What if, let's
We're
say,
not fetching at the same time.
a little bit almost at the same time?
This one.
Okay. Yeah, let's say, like, the second one makes you go.
Why are you causing problem when there is no problem? Did you understand this completely?
No. Yeah.
No. So let's look at the basic. Let me complicate your life. Don't complicate your life for yourself.
And you said the delay would be 1 nanosecond between each?
Updating the PC. Whatever time it takes to update the PC, because I need the next counter. Next counter, next. And we establish that incrementing PC is 1 nanosecond.
Okay, so.
Yes?
So, for each core, it only has like what, the ALU? and-
I did not say anything yet. I have 1 IR. That's all, nothing else. 1 MDR, 1 AMAR, 1 PC. I have not established what it has. I want you to understand this before I add more piece of hardware. Only thing we did is fetch, nothing else. Yes?
You said you moved the PC, when the PC gets implemented to the top of fetch now, right?
Right after I put that into. That's the second line of the code. So I need to push that address in the address bus before I get to the next address. Okay? Any other question? Yes?
This for IR, right?
4 IRs.
Okay, so when you put the,
So,
because earlier you said there's 1 IR.
no, 1 PC,
Mm-hmm.
4 IRs. If I'm doing 4 fetches, I need 4 IRs. Correct?
Mm-hmm.
Where is the instruction being stored? Only thing I did is fetch. I'm trying to do fetch, I should say. Any other question? Yes.
And there isn't multiple MAOs and MDRs, right? Just multiple?
1 MDR, 1 MAR, because I only have 1 bus. I cannot have multiple MARs dropping things into different buses. So I only have 1 bus.
So there's multiple IRs, or is there multiple like ALUs?
The slowness is still there from the bus. But execution of an instruction is much faster on the processor than the transfer. But if I'm sending 4 requests for 4 instructions, they'll all come back in the same order. As soon as they hit the MDR, I'm going to move them to IR. Move them to IR, move them to IR, move them to IR. And that is a change in the processor. I don't know how to do that yet. That's a different design. How many IRs I had before? 1. Now I have 4 IRs, so I need to know which core is the request coming from. Okay, is the request coming from core 1, core 2, core 3, or core 4? I need to keep track of that request. Extra information needs to be there. Don't know how to solve that problem yet, but let's fetch the instruction. Fetching is easy, because after fetching, I need to decode. Okay, I need to decode. Where do I decode from? From the IR. I already have the IR, no conflicts. Look at it, figure it out. Nothing wrong. Okay, nothing wrong with those instructions. So I can decode all of them. No problem, I can do them at the same time. Each processor needs a decoder. Okay, to review or to analyze what the instruction is. Yes?
This is like still using the like half cycle thought process.
I don't need to anymore. Because I have 4 IRs. Yes?
Yeah,
So there is no. This needed that. Yes? This, have all 4 happening at the same time. 4 instruction fetched and 4 decoding at the same time. Is it always possible? No, I don't know. As somebody was overthinking already. What if there is a dependency? Who cares? That's for the final. I don't teach you those, tough stuff. I only ask you how to do those. Fetch decode. Decoding has no dependency on each other instruction, so I can decode all of them. That is good. Let's keep a simple instruction first. All of them are R-type. Okay, all of them are R-type, and if they're all R-type, next thing is exact. So for me to be able to execute 4 R-type instructions at the same time, I need 4 ALUs, 1 on each core. Whatever the computation is, that is happening. Remember, why are we adding cores? Because we want to compute or execute things faster. An L-type instruction doesn't use this cores at all. Because what is L-type doing? Going to main memory and getting data. What's the point of a core for that? I don't need it. Core is I want to compute things faster. I want to execute the computation of things faster. So these 4 R-type instructions, I can run them all at the same time if each of them has its own processor. So I have 1 PC, 1 MDR, 1 MAR. 4 IRs and 4 ALUs. 1 for each core. Okay? None of them are going to main memory. So no operation. Each of them need to write to their own destination. They will do that individually. If they're each writing to their own destination, okay, I need to be mindful of certain things. I have 4 cores. If all of my cores need to be able to use any of the register during the execution, they each cannot have their own register. It better be shared. Just like the PC, just like the MAR, just like the MDR. So the GPR, general purpose registers, that's one set. So any core can update it, any core can use it. These 4 instructions that you just executed here, assumed they all are type. There is no dependency between each of them. Okay? Simple execution. 4 instructions executing in parallel at the same time on 4 cores. So this is a vector pipeline or a super scalar pipeline. Here you have multiple cores. You are able to execute multiple instructions in parallel, truly parallel. This is not like scalar pipeline, where only one instruction was getting fetched. For this to happen, you need to have multiple cores. I designed a core which had 1 PC, 4 IRs, 4 ALUs, 1 MDR, 1 MAR, and general purpose register that are shared. You can have completely different configurations of cores. Some cores have their own GPRs. Okay, have their own GPR and shared GPRs. Cost more because I'm taking the space. Some of them only have 1 IR. So only 1 instruction is fetched, executed, 1 instruction is fetched, but it's getting fetched to different processors within, different ALUs within that processor. Most of the time cores are used for multi-threaded programming. What is a multi-threaded programming? One program having multiple streams of execution, completely independent. Sometimes dependent, but completely independent. So there is no dependency between the part of the code. Because as soon as I started introducing dependency in this stupid code, superscalar can go out the window. Superscalar will act exactly like a scalar pipeline if I have any dependency here. I can fetch 4 instructions at the same time, but can I execute all 4 at the same time? Okay, that is always the problem, depending on the code. Okay, so superscalar, multi-core, that is there, is super duper version of the scalar pipeline, where I am executing multiple instructions, truly executing them at the same time. This is 5 cycles. If I had executed the same R-type instructions without any dependency, you know it will be 5, 6, 7, 8 cycles. So to speed up, single cycle would have been 20 cycles. Pipeline 8, super scalar pipeline has 5. So you're improving the performance of execution, but you're still executing one program at a time. Yes?
And this, what we did here, this is assuming that there's no dependencies, correct?
There is 0 dependency. We'll deal with dependency on Wednesday.